Hey there, Bill Gerald, Energy and Industry. Once again, I'm Chief Energy Engineer for CalPortland. Working in my office here in Riverside, California. It's actually technically in Urupa Valley, but Riverside, California is the major location nearby. And we call this the Crestmore facility. There used to be a cement plant right next door, the Crestmore cement plant from Riverside Cement. Anyways, I thought we'd take a little adventure today and drive on up to Las Vegas, Nevada, visit our terminal up there. We have a cement terminal, and so why don't you come along for a ride and let's go check it out. Make sure we mask up and do our social distancing. See you there. Greetings, this is Energy and Industry. Hi, I'm Bill Gerald. I'm the Chief Energy Engineer for CalPortland, and today we're in Las Vegas, Nevada. We're at the CalPortland Las Vegas terminal, and we're going to talk about the operations here, their energy efficiency trends, and some of their key practices that have made significant improvements on their energy consumption here at the terminal. So you stand by and watch this video and look at some of the great changes and the great opportunities that you can maybe make at your operations. A cement terminal is an operation where we produce our cement in a cement plant, cement factory, and we have two in California and the one in Arizona. So the two in California are just under 200 miles away down in the Mojave Desert, and we ship that cement up here to this terminal, and that terminal receives the cement, stores it in these silos, and then ships it out on trucks to the local market, either our CalPortland ready-mix plants or other customers wanting the cement either for their ready-mix plants or other customers. The cement terminal is an important feature. It extends basically that cement pipeline from our cement operations out towards the markets where your plant isn't right next door to. This terminal receives cement both by rail and by truck. It'll receive it by both, and then it ships out cement by truck. The operations here are managed by Jamie Padilla. She's the plant manager here, and she has been an amazing asset for the energy department. She really focuses on energy here, and they've done a lot of unique key changes to reduce their energy and make this operation much more efficient. This terminal actually achieved the Energy Star Challenge for Industry a few years ago. That's where they reduced their energy consumption, their energy per ton of moved material. They had a 10% improvement, and I think they actually beat 10%, but the minimum was 10%. And they made that achievement a few years ago, and we're working towards doing that again. Hey, so here we are. We're at the rail unloading station here at the Las Vegas terminal, and you know these cement cars, about 100 tons of cement in it. There are these hoppers at the bottom with a gate, and so the cement's going to go down that gate. There's a hole in the between the rails there. That's where the cement's going to go. There's a boot. It's actually lifted up to make a seal on there. And then the cement's going to flow down in there. Now, cement, it in many cases it will flow almost like water, but it gets stuck, and so you need to shake the car. All right, so these rail cars, they have slots on them, and right there, that's where you put this vibrator. That's a pneumatic vibrator, right? We take air, supply it to the mechanical vibrator, and it actually shakes this car. Okay, so we all know compressed air is super expensive, right? It's an expensive utility that you have to produce at an operation. Previously, what would happen is, in many locations will be the same way, you will run that vibrator constantly. You just let that thing vibrate, shake that car until you unload it. It's easy. What they realized here, Jamie Padilla again, realized that, that compressed air takes us money, energy to produce that compressed air, and we're constantly vibrating this car. It could be empty and you were still vibrating it, right? An operator, turn a valve on, air flows, and you vibrate until it's empty. So where the cement goes, it goes underground, and there are a pair of screw conveyors that are pulling that cement and filling into a bucket elevator. We have monitoring of those screw conveyors, and we can monitor the amps, the load that's going through that motor. When there is no cement, the load will go low, the amps will go low, and the PLC, the computer, will recognize that, and it will turn on a solenoid valve to shake the car. Then as it sees load again, it realizes that there's cement flowing, it turns the solenoid valve back off. So the vibrator is only shaking the car when the system sees that there's no load. You know, obviously you do this until the car is empty, and then they move the car up to the next car, right? So this was a great project, and they shrink down their air consumption by large volumes here, right? It's an amazing change, and these solutions are not very high cost, and it just takes programming, having a PLC programmer. That may be the hardest part. Luckily, in our company, we have automation engineers that are, they're available to do this work. They study it, help out the local team, and do some simple changes and get this kind of a project functional. So here we go. I better take that off so they don't drive off with it. These things are heavy. All right, thanks a lot. We're gonna check some other things out, but once again, automation of compressed air. You can't get much better improvements than picking these two items together. Thanks a lot. Well, here we are. We're down here below the rail cars. This is one of the screw conveyors. There's a pair of them. The motor there at the bottom of that screw conveyor, and right here's where the cement's coming down into it, and it drops down at the end of that screw conveyor into the bucket elevator. These screw conveyors have variable frequency drives on them, a VFD, variable frequency drive. What that is it's very common in the industry now, but I thought I'd talk about it. It's a device that takes the line power coming in from the utility, converts it to a new AC waveform, alternating current waveform, that we can control the frequency of it. And with alternating current motors, when you can control the frequency, you can control the speed of the motor, right? So This motor can be ramped up and down in speed depending on what the requirements are, right? If you just put in a standard motor, 60 hertz, 60 cycles per second is the United States common frequency. We can vary that frequency to different levels to either high speed moving that material, or slow it down. And the benefit of this is when you can control the speed of that motor, you're not wasting energy for excess speed when you don't need it, right? This is, it's much more common in energy efficiency in the fan operations, when you can control the speed of the fan. Affinity laws say that you can get a cubic function of savings from the airflow to the energy consumption. It's a cubic relationship, so that means it's tremendous savings, huge savings. So I just wanted to point out the screw conveyor, the fact that it has a VFD on it, and all the automation that goes into the unloading of the car to the bucket elevator and controlling that speed and moving the cement as efficiently as possible. Once again, it's a tons per kilowatt hour energy metrics. That's our energy intensity, and we want to minimize our it's kilowatt hours per ton. It is a kilowatt hours per ton energy metrics. How much energy per unit product? And here it's the tons of cement. Let's see what else we can find. Okay, here we have the terminal behind me again. Rail cars on the right side over here, truck traffic on the left side, and we're looking right down the pathway, through the terminal. Now, the very tall structure right here is a bucket elevator. So when the cement is unloaded from the rail cars, goes underground, goes through a pair of screw conveyors. Those screw conveyors are moving the material to the bottom of that bucket elevator, and the bucket elevator is lifting it up to the top of those silos, and then we have gates and movements to move that to different silos. All right, so a couple of good things about this bucket elevator. So when this project was being for installing this bucket elevator, and originally the three shorter silos, those were the original terminal silos here. Well, they wanted to add storage to the operation, so they built these two larger silos, and you need to convey that cement to the top of the silo to fill it. Very, very common in the cement industry is use pneumatic conveyance. The capital is cheap, and you just got to buy a compressor, a pump, put a 4 or 6 inch or 8 inch pipeline, go to the top of that silo. It's capital-wise, the cost of install is cheap. Much more expensive to install is put a bucket elevator in it, a mechanical conveyor, and lifting it up, mechanically. With CalPortland and the way our energy program is important to us, and our engineering group, we work closely and tightly together. We look at these and make sure that we're putting that capital money up front, because the lifetime savings is significant. Running that compressor and that pump for the next 20 or 30 years, the energy consumption is tremendous. We're going to have much less energy consumption putting in this bucket elevator in. You just have to put that money up front to get this installed, so that you're conveying that cement mechanically. Everywhere we can, if we can convey cement mechanically, we will. Sometimes pneumatic is just the only way you can do it, but if we can, all our new projects, we try to get mechanical conveyance. All right, so that's one item. Now that same bucket elevator, so as the rail car is unloading, going through the screw, and then feeding up that bucket elevator, so it's running. Think about it, it's running all day long, operating. There's a control room, in the building, in the administration building here, and they start and stop equipment. Now, typically that bucket elevator was just running constantly, because as you finish up a rail car, then the operators have to go move the cars up and back and forth, and maybe even there's cars all over this property, right? So it takes them time to get these cars moved around to get the next car in an unloading position. All that time, this bucket elevator would still be running. You know, it's running empty, but it's consuming power. So they implemented a program where, once again, automation. They monitor the bucket elevator amps, watch that load. As the load drops and falls down to an empty condition, a timer starts. So this timer is waiting to make sure, okay, is this really empty? Is this not just a bump in the system, the rail car stopped flowing or something like that? It has a amount of time, and that's an adjustable time that they can, you know, fine tune. But after a certain amount of time, the bucket elevator will go ahead and stop running. So then they'll need to restart it later on to unload, but it's going to, all that downtime in between moving cars around, automatically shutting down that elevator is going to be you know, a fair amount of savings, and an important feature of this operation is, once again, they are constantly looking for ways to save energy here, and look at you know, using automation, using, you know, they're understanding the operation to reduce their energy consumption. So that's the story of the bucket elevator, and it's another great project. And kudos to the Las Vegas terminal and Jamie Padilla again for always thinking and looking for those ways to save energy. Okay, here we are at the compressors for the terminal. They have two Gardner Denver compressors supplying the compressed air to all the operations of the plant. Things like dust collector pulsing, gate moving for the opening and closing gates that move the cement around, the truck loading operation, lots of equipment require the compressed air here. So, you know, if you go way back, and maybe you go to almost any facility in America, turn that compressor on in the morning, just let it run all day long, making air, right? Well, if there's not a truck unloading, if there isn't a rail car unloading or loading, if there isn't some kind of movement of cement in and out of this terminal, why does this compressor need to run? You're essentially supplying leaks. The only purpose of this compressed air is to help move cement. So this plant, they implemented a feature where this compressor is automatically watching that scale. It's looking for a truck. Is that truck here to be unloaded? And it won't turn that compressor on unless it's being unloaded. Now they have the other, you know, automation lets you have lots of possibilities and use a lot of tools. They do need compressed air for unloading the rail cars. So that's all part of the algorithm. Looking, do I have a rail car? Do I have a truck to unload? It's being smart. It's a smart system where it's looking for, do I need to run my compressor right now? Is there a functional purpose? And having that kind of a setup reduces the hours on this compressor. And for those that are you know, in charge of compressors, we all know that maintenance of them is very important, and bringing in somebody to do maintenance, filter changes, oil changes. So reducing hours helps you on your maintenance. And obviously, it's going to reduce energy. Minimizing those hours reduces the energy that we're providing to the system to compress air to that higher pressure set point. So, you know, great job. And what's been great here, been around this place a long time, and these are compressors been here a long time. They, you know, minimizing those hours lets them last. They're durable and they last a long time because they got minimal hours on them. You know, good job on compressed air. Hey, so I thought this would be a good opportunity to talk about dust collectors right now. So we have a lot of dust collectors in our operations all across CalPortland properties, and I've said it before, it's essentially a vacuum cleaner, right? And this, like most traditional vacuum cleaners, there's a bag and it gets full of material, right? In a dust collector's case, so we have this box here, there's a fan pulling air through the silos, the conveyors. It's sucking the air off of those areas, and the air is being pulled through this box. Inside of it is a filter. Usually they're a long cylindrical filter. It's got a cage, typically a metal cage, and around that cage is like a sock. And that filter is where the dust or the product is being collected, and the clean air goes through the inside of that cage or that filter, and then it goes out the ventilation stack cleaned up, and we've collected the material, that fine product. So as the bags are collecting that dust, it gets covered in layers of dust, and then the suction goes down, right? Because now you're restricting airflow. So what you want to do is how can I get this dust or material to fall off that bag? There's different things. There's shakers, right? Where a mechanical shaking of a bag will shake it off. There's something called reverse air bag houses, where they actually open and close dampers that will collapse that filter, and when it collapses it knocks off that material, then it reinflates that bag and then puts it back in service. This is where typically a multi-section dust collector bag house would be doing that. These pneumatic dust collectors, they use compressed air. What you're seeing right here is the diaphragm right here, and on the top here, this is where the compressed air is coming in. There's basically a small little, it's essentially a receiver, but it's got compressed air in there. And there's a little control line right here. And that control line is also pneumatic, it's just air, but in a junction box around the corner are solenoid valves. When a solenoid valve is an electrical valve that it gets an electrical signal to open up mechanically to let air to flow through. Well, when that solenoid valve is actuated, air is then allowed to move in this line, this very small line. There's a diaphragm in there that it makes a movement, and then it allows that compressed air to flow from this diaphragm internally inside. And there's an air line right there. That air line goes inside, and it blows down the center of that filter bag. It just is blowing compressed air, and it makes a pulse of air, and it pops that bag. So when it pops that bag and inflates it, material falls off. At the bottom of these dust collectors are hoppers, and there's a method of collecting it, either a rotary feeder or a rotary valve or tipping valves, all kinds of mechanical ways we collect it and then put that material back, either back into service, into the materials, or collect it as dust and find different ways to handle that. But for this topic, that compressed air is used to time, to periodically blow down these filters to keep them clean. There are times when you find a dust collector, you power it up, and it's got a fan that's pulling air through, and the only other electrical component is the timer card, which is timing the pulsing of these bags. Old vintage timers where basically it's a circuit board that just, you set the time and it would constantly pulse. Pop, 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 pop. You hear a popping sound when it pulses. And have you noticed you have not heard a popping sound, right? One of the first methods of minimizing that compressed air consumption in a bag house is, if the fan is not running, do not operate the timer. A lot of places what we have is we have a 480 volt to 120 volt transformer right at the motor. So when the motor's getting power to run the fan, that power is then sent to the timer card. That's a very effective way of controlling those timers so that they only operate when the fan is running. Now, when it is running, when this timer is running, once again, you could just be constantly, sending air to clean these bags. Well, what if there really wasn't a lot of material that's picking up? What if it really just wasn't a dusty environment that bad? Well, you might extend that timer so that it only times so much, or you might pull it back and time it a lot because it's worse. Well, once again, automation. What you do is you monitor, and here we have the lines right here, and there's a clean side and a dirty side of the bag house. You monitor the differential pressure across that. You measure pressure on both sides of that filter. When there is lots of differential pressure, that means the bag is starting to get covered out and getting covered with material. So you make a set point. Newer timer cards have a differential pressure input into it. And you can make a set point that says, for so many inches of water of differential pressure, I will pulse. When it gets below that, the filter's clean, do not pulse it, right? So having a timer card with differential pressure input is very valuable in the energy efficiency world, because you're monitoring that differential pressure, making sure because once again, we're using compressed air, super expensive product, and guarantee there's thousands of dust collectors out there across this country that have a timer card that is constantly running. First thing I do when I go to a plant, if it's a new plant especially, my ears are listening, and a lot of times the dust collector is top of a silo. It's way up there, it's hard to get to, it's ignored, because you need environmental compliance, so you leave it alone. But if you're constantly, cleaning these bags, not only is it's wear and tear on the material, wear and tear on the diaphragm, the bag itself, the filter gets worn out because it keeps getting that transitional, compressed air blowing into it. We're consuming energy to make air that we didn't need to make. So there's all kinds of reasons why to automate these timer cards, so that you only operate, you only pulse the bags as necessary. And like I said at the beginning, don't turn the timer on unless the fan is actually running. Complete waste of time when you're popping and cleaning bags that are not collecting material, right? These are small nickel and dime, cuts of many, thousands of cuts to kill you, right? And so, focusing on these is important for us, and getting them in a condition where all the things I just described. So, dust collector. Bill Gerald here, Energy and Industry. We're at the Las Vegas terminal, the CalPortland Las Vegas terminal, and we have here is Jamie Padilla. She's the terminal manager, and we're going to ask her a few questions about our operations. So first, to start off, Jamie, what is your background with CalPortland?
Yes, so I started with the company in June of 1999, and I'm a third-generation employee. My grandfather worked for the Colton plant and then went to Mojave, and my dad worked at the Mojave plant. And I actually started at the Mojave plant as a summer laborer, and then had the opportunity to apply for this job, and here I am. Been running the terminal ever since, and we started as groundbreaking here. When I first came on, it was just ground, and we brought it all up. So it's been fun to see the whole process from the get-go. We were designed to ship 400,000 tons through our terminal and unload rail. And we've streamlined that rail to we unload rail cars in about 10 to 15 minutes. And we store them in our silos, and we hold just under 10,000 tons storage capacity. And then we load them into bulk trucks. And you can see we're loading a truck right now. And it takes us about 6 minutes. And then those loaded bulk trucks go on out to the batch guys, and they make the concrete. So our terminal is a little unique in the point of view that we also load gypsum back into the rail cars, and that goes back to both of our plants for the raw materials.
So. That's great. I'm a second generation CalPortland employee as well, so it's always great to hear about other employees with that background.
Yeah.
I think it's a great asset to our company and the longevity of our all of us being in the company. Okay, back here at Las Vegas terminal with Jamie Padilla, and what she's holding is the Energy Star Challenge for Industry recognition from Energy Star. The Challenge for Industry is a program where plants can enter into it and try to achieve a 10% energy efficiency savings within 5 years. And this terminal, Las Vegas terminal, achieved this in 2012. And it was actually one of our first facilities in CalPortland that achieved this goal. And
Yay!
yeah, exactly. So I just wanted to make sure that Jamie, they did a great job here and getting the facility, all these reductions that they've gotten, and they've just done so much more since then. And I believe this is actually back in the challenge again. I don't know if you knew that or not, but
Yeah.
we're back in the challenge trying to get 10% again from where the baseline was set when we started again. So any thoughts on that, Jamie, or any last thoughts on our visit here and on the challenge for industry?
Well, I think it's kind of fun to continue to think about it because it's easy to get the low-hanging fruit, but you have to really challenge yourself to think of other things to try to think about, like our eco elevator and turning off the vibrators when just use the gravity feed. So sometimes they're really simple things, but we make them complicated. So I would challenge you to look for things that are simpler than what you think.
Do you find the recognition helps, at least as far as a human being being recognized for achievements? Does it help you motivate you or motivate people in the plant?
I think it motivates the crew because they enjoy seeing positive feedback on their efforts that they've put into their job. Our job is one of those that we want to never see the product. It comes in and goes out. We never want to see it. So sometimes we don't realize how much work we actually do. But when you actually do a project outside of what we do on a normal basis and we get to see rewards, I think it helps motivate the crew.
That's great. Well, thanks for letting me come in today and visit your plant and check out all your energy efficiency projects.
Well, thank you, Bill. We appreciate you coming and hope you enjoyed Las Vegas.
Yep.
At least the weather.
Yeah. All right, thanks. Bye.